Hey everyone, Happy New Year! For episode 1 of 2024, we interviewed Joshua Kerber with the state of Minnesota, and he shared some fantastic information. I mean, this was just solid gold from an educational standpoint. And he, starting around the 6-minute mark, he shared a slide deck with us, and I thought this would be really helpful for the listeners to follow along with. So I kind of pirated his slide deck, and he gave me permission to share it. So I put a link to this slide deck. I got it on Google Slides. I put that in our show notes. You can find the show notes if you go to structuretalk.com. You click on this episode, you can get a link to it. It's really helpful to follow along. We get into some really technical content here, but it's worth it. I hope you enjoy this educational content as much as I did. All right, back to the show. Welcome to my house. Welcome to the Structure Talk podcast, a production of Structure Tech Home Inspections. My name is Reuben Saltzman. I'm your host, alongside building science geek Tessa Murray. We help home inspectors up their game through education, and we help homeowners to be better stewards of their houses. We've been keeping it real on this podcast since 2019, and we are also the #1 home inspection podcast in the world, according to my mom. Let's go. All right, welcome to the show where we talk about home inspections, houses, and anything else that's rattling around in our heads. Okay, that was a callback to Bill. I just got done listening to an episode that we did with Joshua Kerber from the state of Minnesota. He's the head honcho when it comes to radon at the state. And he's laughing. And we had him on 2.5 years ago now it was. 2.5 years ago. Where does time
2021.
go? At the end of the show, we said, all right, we're going to have you back on real soon. And boy, does time fly. So here we are 2.5 years ago. But before we get into Josh, I got to share a follow-up because Tessa, you and I talked about my devastating Christmas light fail. Josh, I was installing these permanent LEDs on my house, and it is a project to put those on. They just stay on forever. And I didn't successfully do it. I cut them. I didn't follow the manufacturer's instructions. They said, don't cut them. I cut them anyway. And I learned how to do it, but I did it wrong and they didn't work. And then they were on back order until January, but they came early. And then we had some unseasonably warm weather and I was able to complete the project and it's done now. So just had to share that little win for anybody who didn't tune out before that last episode was over. My Christmas lights are up and they work. So,
Can I just add?
Yay me!
Can I just add? Your face, Reuben, is the best. You're like a kid in a candy store when you were sharing that epic win. Because if anyone hasn't listened, go back and listen to the episode about the Christmas lights. I think we have. We just recorded that a couple weeks ago, but Reuben, that was like the most epic story I think I've ever heard you share. It reminded me of National Lampoon's Christmas Vacation, where he spent all of that time putting lights all over his house and then he goes to plug it in and they don't come on. It was like that, but you never have fails. You always succeed in any home project you take on. This was the first time I think you got into a position where you failed. Sorry.
Yeah, that was frustrating.
I wish I could put it a little bit, but it's pretty blunt. You did. You couldn't complete the project and it killed you.
It did. But they're done before Christmas. So happy day. And
congratulations.
Although, you know what, when this one airs, normally we air our podcasts on Mondays. So we're probably not going to share this one for a while because I'm not going to share the podcast on Christmas Day. And I probably won't share it on New Year's Day. So you're going to hear about this like January 8th or something when we share our podcast. But as we're recording, it is before Christmas. All right. That's enough to do about boring Christmas light story. Let's bring Joshua on. Josh, I know your official title at the state is not head honcho. What's your official title there?
I'm a research scientist at the indoor air unit at the Minnesota Department of Health.
Okay. All right. We'll go with that.
I'm one of many honchos or people, let's just say, not the head by any means. I might have the biggest head, but I'm not the head guy.
And what do you do there week in and week out?
Week in and week out, I help to coordinate both our outreach and education program as well as dabble a little bit in our enforcement and regulation oversight program. I'm also chair of what takes most of my time is the current chair of the state work group for radon programs. So we're dealing with a lot of national issues as far as that goes. So kind of hold a whole bunch of different hats, keeping a lot of plates in the air.
Okay.
Can you give us an example of like a national issue you're dealing with?
Multifamily radon testing. If you're dealing with a project from HUD requires you to test 100% of ground contact units in multifamily buildings.
Okay.
However, they only hold about 10% of the federal mortgages on multifamily buildings. The other 90% is under Fannie Mae and Freddie Mac, who recently changed their policy from testing 10% to testing 25%, which is still not nearly sufficient in order to accurately identify problems in buildings. So it's getting the education out on that. Hopefully over time improving that policy. So anybody who's living in a multifamily building at some point will have some sort of radon protection, because renters don't really have any say in their radon levels, right?
Yeah. Huh.
Gotcha.
So this is going to be a national. This is a national law. It's not a state by state thing.
Right. It's a national policy. It's not a law. But if the mortgages were going through Fannie or Freddie, these things should be checked.
Interesting.
Gotcha.
Okay.
Okay, cool.
Thing to keep an eye on going down the
Josh,
pipeline.
when we left off on our last podcast 2.5 years ago, we had teased this show by talking about some potential case studies that you had to share with us. And I'd love to pick up right where we left off.
Okay. We can certainly do that. I've got a bunch of them. I've got one in particular I'll pull up.
And for anyone listening, if you don't know what radon is, or you want a little bit more background, go back and listen to the other show. We're not going to repeat all of that other content, but Josh had a lot to talk about as far as radon in Minnesota.
So this is actually a presentation that me and a colleague, co-teacher from Kansas, we do some training on optimal mitigation and system design. And so I wanted to get into this because it's becoming more and more important to properly size radon systems, because they're not all a one-size-fits-all approach, even in new construction, which this is the example of. So here we have I got to remember to talk to people that can't see these screens. We're looking at a 2020 new home build in the Southwest metro area, Scott County to be specific. It does already include passive radon control methods because it was built to the state building code. It's a 1,900 square foot basement footprint, full basement, poured walls, poured slab, and a very conscientious builder. So a lot of the details, a lot of attention paid to a lot of the fine details. It's a super tight house. The blower door was a 1.05 ACH 50. So it's one of the tighter houses I've ever worked on. And there's a lot of really neat dorking out kind of building science stuff that we'll get in here. And it does have a 3-inch passive riser, passive radon pipe coming from the drain tile and exhausting through the roof. So what we like to do when we get to projects is we do pressure relation measurements through the floor. So we're measuring the pressure the house is exerting on the subslab material in relation to the basement. So is the air from the soil wanting to come up through the floor, or is it going down into the floor? Now radon enters, actually let me ask this to Reuben or Tessa, why does radon enter a house?
Houses are generally under negative pressure in the basement. You got stack effect. Air wants to go in at the bottom and it usually wants to leave at the top.
There you go.
That's simplifying it, but
it's simplifying it. I can simplify it even easier. Houses suck.
that was on the tip of my tongue. Yes.
And if you want to get into the nitty gritty, schools blow. So So anyways, what we find here, and this is very common in many homes, is that we're measuring the pressure gradient between the basement air and the subslab air. We do that through a small hole we drill through the floor, usually say 3/8 inch of a hole or half-inch hole. And we use digital micromanometer pressure gauges to measure these small pressure changes. I like to use the international unit in pascals for pressure differences because it's just easier. They're usually whole numbers or only one decimal point. A lot of American mitigation contractors will use inches of water column, which can go to 3 decimal places. And the more decimal places I got to monkey with, the greater chance I'm going to have an error. So I try to just keep it simple. But for those that want to know, it's about 250 pascals in 1 inch of water column. So you can do the conversion if you want to as we're going. In this particular case, we drilled 4 holes basically in all 4 corners of the basement, and we got a background pressure reading at all 4 locations. And the pressure readings range from positive 1.5 to positive 1.9. So what that tells me is that the house is sucking on the soil at roughly 2 pascals at the strongest point. The initial radon test in this home came back at 10.7. So we need to activate this. It also shows that even though we build houses to the building code and they're built what's quote unquote called radon resistant, some of them still fail the radon test. And this is an example of that. But the good news here is that you can fix it so simply. So we activated we activated this radon system with what is considered a mid-range fan. It's kind of the most oftenly used type of radon fan. All three main radon fan manufacturers have a mid-range fan. They draw roughly 50 watts of power, and they can move 100 and 120 CFM if they really need to. So we install that fan on this system because it's the most commonly used type of radon fan. Maybe 2/3 of our systems in Minnesota, gosh, maybe even more than that, will have a mid-range fan used on it. So very, very common. And what we found is that when we put the fan on, we get very good pressure field extension, and we turn those positive numbers at the test holes we were looking at from positive, say, 2, we now change them to negative 55, negative 70, negative 106 at our strongest point. So with those negative numbers, that tells me the radon system is capturing the entire subslab area. So our radon collection should be very strong. We do that with airflow of 65 CFM, and we can measure that through the pipe. And we're using 52 watts of power. So with those 2 numbers and one assumption, we can calculate the total system operating cost of this radon system. So we are winning the radon game. I know that because we retested, but 2, there's negative pressure under the entire foundation, and that's what you want to see. So we know we're winning the radon game. We know how much airflow we have, and we're losing. I'm kind of giving this away. Where does that airflow in radon systems come from? Not a rhetorical question. Asking you two. Do you know where it comes from?
I'd say there's got to be gaps. Yeah. There's got to be gaps in the home that allow air to go under the slab. It's got to be coming from the house.
Got to be. In many cases, it absolutely is. You can measure that too, and in this case, we could. I'll spare the details on that, but rule of thumb for figuring out operating costs is we just assume half the radon air or half the air in the radon system is coming from the house. In some cases, all of it's coming from the house. So imagine we're kind of building the case here about this might be a little bit more interesting than meets the eye. So 65 CFM at 52 watts. At the radon level at this point is less than 0.5. So we fixed this house at 65 CFM, 52 watts. We've got a calculator here where if we know how much air we're pulling from the house and we know the climate data, the efficiency of our different appliances like our furnace and our air conditioner, if we know the cost of gas, the cost of electricity, we can calculate the total system operating cost of this radon system. And in this case, I'm assuming of that 65 CFM, 45 of that is coming from the house. Knowing all the information as far as the efficiency of the gas furnace and the SEER rating of the air conditioner, plus the wattage of the fan, it's $183 of conditioned air going out the radon pipe every year. In addition, it's 52 watts of power, which is, if you do the calcs, right now the cost of electricity is roughly 1 watt equals $1 annually. So 52 plus 183 is $236 a year to run this radon system. And when you look at the pressure numbers that we induced, we're actually overkilling this radon system. We're getting like 60 pascals negative. We only need 5. So what's a good solution? Good solution to optimization is using a smaller fan. So we switched out the medium range fan and we went to a low wattage fan. Obviously, low wattage is going to use less electricity. It's going to operate at a lower total airflow, and it's a heck of a lot quieter. The fan itself is quieter, and the airflow coming through the pipe, because the air is reduced, that airflow noise is reduced as well, so it's quieter. When we put that fan in, we lose about half our pressure, but we're still really kicking butt as far as radon negative pressure goes throughout all over the slab. Our weakest point is now 27 pascals. So we're still kicking butt. We don't even need 27. Again, we need like 5. But what we did is we reduced our airflow to 32 and our consumption, electrical consumption, to 18 watts. So when you go to our calculator again, let's assume 20 CFM of this system is coming from the house. All the same calcs from the air conditioner efficiency and the cost of electricity. The added ventilation is reduced down to $82 a year, and we're only using 18 watts. So that's an annual cost of $100 a year to run that system. And all we did was switch to a smaller fan, and that smaller fan is still winning the radon game. So an important point of system optimization is just using the proper fan. Just because it's the only one you have on the just because it's the only one you have on the truck doesn't mean it's the right fan.
Right.
Sure.
Okay.
Well,
so
not only are you saving money by switching to a smaller fan, but you're probably less likely to create other combustion safety issues in the house by not having such a strong negative pressure as well.
Absolutely. Then I wanted to make you guys aware that there's emerging technology in the radon mitigation front. Speed control or electronically controlled fans are becoming more and more popular. And it's a computer chip inside the fan that triggers magnets to kick on and off at a certain rate to spin the impeller and make the fan run. Well, the cool thing about that is that you can drastically cut the electrical operating costs of these things. So we switched out that low wattage fan for one of these new dialed down adjustable speed fans. And we dialed that down. There's a dial in the electrical control box. You can turn that down all the way till you're just getting the pressure difference in the far reaches of the basement that you want. So that's what we did. We dialed this down, so we're getting 5 pascals of negative pressure everywhere. We are winning the radon game. We are only moving 8 CFM.
Wow.
A late friend of mine says 8 CFM is more like a gnat fart. Tiny amount of air. But would take a guess at what the wattage was to fix this. 8 CFM.
No idea.
2 watts.
Yes, 2 watts.
Yes.
Nice.
That was totally off the cuff too. We did not practice that.
No.
2 watts. Yes, it's incredible. So
Oh my goodness.
smaller amount of energy than you could ever imagine. We could fix this house just for grins. We put it through the calculator, assuming half the air is coming from the house. So 4 CFM, that's $16 a year, plus $2 for the fan. That's $18 a year to run this
Wow.
radon system.
Fascinating.
All right.
Josh,
So
can I ask a
let
quick
me
question?
just Oh, go ahead, Tess.
I was wondering, are these adjustable rate fans, are they something that like you have to manually adjust, or are they smart enough that they can adjust up or down to keep it at a certain flow rate or pressure?
Right now it's manually adjusted.
Okay.
But I could see some automation coming down the pipe. No idea what that's going to cost. Now, these adjustable speed fans, they're about 2x the cost of their non-adjustable counterparts.
Yeah.
So a mid-range fan is about $125. The adjustable side of that is $250 or more. And there's different sizes of these adjustable fans too. We just demoed the smallest of the versions that are out there. But to recap it, we went through 3 different setups in this house, and all 3 setups fixed the radon, but at 3 different costs. And each fan should last at least 10 years. So in our training radon world, we tend to talk about 10-year operating costs. So if you take the mid-range fan example, it was $236 a year times 10 years. Without adjusting for inflation, it's almost $2,400.
Mm-hmm.
If you just switch to that low wattage fan, which still fixed the house, that 10-year operating cost is only $1,000. And then the dialed down adjustable fan, which uses a tiny amount of wattage and a tiny amount of air, only going to cost $180 for 10 years. But there are limitations to this. Okay, this example was meant to show potential savings. When you're dealing with such low wattage and such low airflows in a super tight house, what happens when someone starts to live in that house? They turn on an exhaust fan, they do a load of laundry, whatever it might be. When we're talking such small margins like this, operation of the building can overpower a radon system. So while we dialed this all the way down to just borderline, we can't leave it there. We got to have a little bit more power behind it. And so that's what we did. We actually dialed it up to about 6 watts. 6 watts and 12 CFM fixed this house.
6 watts and 12 CFM. Now, Josh, is there a way to like seal the subslab from the house, like to reduce the amount of air communication between the two? So when you're in a really airtight house and you turn on a bath fan, it's sucking air from the subslab because it's such a tight house, and it can cause the radon system to not work properly because it's all communicating, all connected. But is there a way to like really seal that subslab from the house so that doesn't communicate and that doesn't happen?
Is there a way to do it 100%? No, there's not.
No. Okay.
The main reason is because there's 2 types of concrete, right? Concrete that will crack and concrete that has cracked and concrete that will crack. But you can seal the basement slab and foundation walls as tight as a drum. And this house has that. But when you do then, you're going to miss some things. There's gaps and cracks you can't see, you don't see. Mm-hmm. There's others that were formed later. So sealing is not a standalone technique, but sealing is a very important optimization activity because it's going to reduce the amount of available air for that radon system out of the basement. And the better you do at sealing, the further you can push your pressure field. So there are example case studies we have where we put in 1 suction point, we turn on the radon fan, and we're doing diagnostics. That's what I described here, doing diagnostics and taking that pressure reading from all 4 corners. And you can watch the pressure numbers increase as you do sealing, as you seal that floor wall joint, or you seal that expansion joint, or the plumbing knockout, whatever it might be. The more sealing you do, the more effective your radon system is going to become. and the less indoor air you're going to suck it down into those holes and ultimately vent it outside.
Mm-hmm. Mm-hmm.
So kind of a good segue. What we ended up doing with this house is we did data logging for weeks at a time. So we have pressure numbers, we have radon numbers, and we can kind of compare when there's activity in the home to how that reflects on our pressure graphs. And what we saw was after we dialed the system to where we wanted to leave it, it controlled the pressure all the time, really, no matter what the homeowners did. But for grins, we set this house under maximum depressurization. And what I mean by that is we took every exhaust fan, the water heater, the dryer, kitchen exhaust hood, all 3 bathroom fans, turned them all on at the same time. And I could get that house down to 47.5 pascals negative.
Wow.
It's so tight that the
Wow.
homeowner can actually do his own ACH 50 test if he really wanted to.
Like a
Just
blower door. Yeah.
just with his existing fans.
Yeah.
So if the homeowner, this weekend, if this homeowner is cooking and has people visiting, and they're showering, they're cooking, maybe doing laundry, that type of activity can overpower some radon systems for a small amount of time. But it's the point of this discussion is to show how important it is to optimize systems, because houses are getting tighter and tighter. So we need to know what we're actually up against from a pressure standpoint. How much airflow do we actually need? You don't want to oversize it, just like air conditioning systems. You don't want to put in something that's too big. You want to put in something that's just right.
And it seems to me even more important now to have a modulating system that's automated, because houses are dynamic and always changing, and that pressure is always going to be changing.
That's very true. The problem is there's not enough money in the radon world to kind of spur that innovation. I think it would just cost too much at this point. But there are other ways that we can optimize systems too with stuff that we already have on the truck. So if contractors and homeowners didn't want to spend 2 times as much money on a fancy new fan, they can optimize systems in other ways. The best way to optimize a system is to restrict the amount of airflow. So if we go back to our very first example where we used a mid-range fan on the radon system and we were getting like 60 pascals negative pressure, if we just cut the airflow in that pipe by using a damper of some sort, it could be a gate valve, it could be a ball damper. There's pros and cons to these, but if we can cut the flow that's coming through these systems, we're going to cut the operating costs. So that's what we did. We put in a gate valve and we dampered the system down to an airflow of 20. If you recall, we were moving close to 60 CFM the first go around. So we cut the air by roughly 2/3. When you reduce airflow, you're also going to reduce the electrical consumption of that fan. So the wattage went down to 40 watts. And if you put that through the calculator at 13 CFM from the building, that's $53 a year of added ventilation. At 40 watts, that's $93 total to operate this system, as opposed to $230 in a system that doesn't have a damper. The only thing we did was damper this down. And
does
it
adding a
takes
damper short? Oh, sorry to interrupt. Does it shorten the life of the fan, putting a damper on
No,
it?
it does not. As long as there's
Okay.
ample airflow going through the fan to keep it cool, and 13 C or what are we at 20 CFM is more than enough air to keep that cool. There's no problem with that. So we went from 230 to 93 just by adding a damper, and it should be something that these contractors have on the truck all the time. Then to save even more, we could use the lower wattage fan. So we swapped that out and dampered it down, and we're still getting negative pressure everywhere. We cut our flow to 20 CFM at 16 watts, and you put that through the calculator, and that comes out to about $69 a year because we added the damper, because we're saving some of the conditioned air and keeping it in the basement. So all told, we've got 5 iterations that we can look at and over a 10-year operating cost. The mid-range fan, again, was $2,360. The high dollar dial down adjustable was only $180, but then you've got stages in between where even with the mid-range fan, if that's the only fan a contractor has on the truck that day, if he can just put a damper on it and not pull so much air out of the basement, he's going to save a lot of money. We can go from $2,360 down to $930 just by adding the damper. And likewise with the low wattage, we can go from $1,000 over 10 years down to something closer to like $700 over 10 years. So it doesn't take a long time to do all this. It takes a little bit, maybe another hour to do some pressure and airflow measurements when you're on site. And then that extra labor is going to be saved very quickly. And so it's a very important piece that we really strive from an optimization standpoint to kind of hammer across. And don't just throw in a mid-range fan because you think it's the right fan and run for the truck. Please employ a lot of contractors to like do this, it's the right thing. Obviously, if we're buying and selling houses, you're probably going to be able to afford these operating costs. But what if these systems are put in a multifamily building or a rental of some sort? Who's covering these electrical costs now? It's a renter. And so is it really fair to assume that someone's always going to be able to afford these operating costs just to reduce their lung cancer risk?
Yeah.
This is fascinating, Josh. Then this is a course that you guys teach to licensed radon. I'm not going to get the term right. Mitigation installers or whatever it is.
It's pieces and parts to it. This is actually a snippet of a more advanced class that I help co-teach through the Kansas State University that I hope to bring up here to Minnesota sometime in 2024. And it would be for credit for our licensees. A lot of our licensees have heard me say a lot of this stuff before, and a lot of them do practice this too, which is great. But there's a lot of turnover too in the radon world and employment. So just always want to kind of keep that out there. So when you guys are out doing your home inspections and you see radon systems, I hope you're also looking for openings through that slab and noting that on your inspection reports. So you can save money and maybe make systems more effective too.
Yeah. Yeah. Well, and I mean, this is eye-opening for me because what I've always told people is, look, you're buying a new house and it already has a passive system. They've been required since the summer of 2009. You got to have a passive system in there. It's still a good idea to test for radon, but worst case scenario is you got to put in a mitigation system. You got to put in a fan. Everything's already there, but you put in a fan, you put in some alarm. It's required to let you know if your fan stops working. The electrical's already done in the attic. You can pick up a fan at Menards for $150 or whatever. Just about anybody can get up there, cut the pipe, throw the fan in. It's not that big of a deal. Handy homeowners like me could even do it. And it's going to fix your radon issue. It's pretty much a guarantee. And this has been my understanding of what it takes. I had no idea that you could be wasting so much conditioned air and just overkilling it by so much if you're not doing any of this diagnostic testing. And I think it really does make a huge difference to hire somebody who knows what they're doing, who's going to do that diagnostic testing. Of course, they're going to charge a few $100 more, whatever it's going to be. But over the 10-year lifespan of that fan, I mean, you're going to totally get your money back for this, right?
Absolutely.
Yeah.
Okay.
And I was going to ask you, Josh, like what percentage of these mitigation contractors out there, are doing this testing, this extensive testing and have a variety of fans to choose from? Would you say the majority of them are aware of this and know that and then can, install a customized system and fan that's best for that house? Or would you say the majority of them are not doing that?
I would say the majority are not doing this. Certainly they're not turning a house into a science project like I do. I don't expect them to do that. But I would say a good quarter of them are doing this on a lot of their systems. Do you have the ability to do this on every system? No, I'm not naive enough to think that it's going to work every single time everywhere. Sometimes you're in tight soils. Sometimes you need to close. Sometimes you need a higher wattage fan that's going to pull harder. I get it. But in the example or the times where you do have the capacity, you now have the wherewithal to actually do it properly or better. Let's just do it better. So yeah, that long answer to that question is most are not doing this, but also most are not charging accordingly to do this. I mean, if you're going to give a phone bid for $1,800 and all of a sudden you get on site and there's a crawl space that you weren't aware of, and then now your margins are even smaller, you're going to lose money on this project. And then we're asking you to spend another hour or two doing all that dialing in. May not be feasible in some cases, but it does also implore them to know what they're getting into. And so, yeah, that system is going to be more expensive, but in the long run, it really won't be.
I got a question for you, Josh. I'm thinking through what I might see, because I've never seen anybody install a system like this where they've got a damper on there. And you're describing a damper as maybe just a gate valve or a ball valve on your PVC tube. So this is going to be a gigantic valve. I know that if I saw that, no?
I don't think they're gigantic. If you give me a minute, I'll run to the garage and get one for you.
Okay. All right. Sounds good. Get it for me. I'm going to pause the show there. All right. Josh is back. And he's got his valve. Let's take a look at it, and I'll describe what it looks like.
All right. So I kind of lied. The only one I have is a 4-inch valve.
And what Josh has here is a gate valve. It's got this T handle, and it's got a rod, and it opens and closes a gate. That's it. And like Josh, I saw this on a house once. One of the inspectors on my company took a picture of that in an attic. And we had a long discussion amongst our team on why that was there and what it was doing. Why the heck would they put a gate valve on a radon mitigation system? Under what conditions would you ever close this? We were all totally scratching our heads, wondering what the heck is this doing on there. Now I know.
Yep.
They're doing it to throttle the system down. But I'll tell you, if I saw this and I'm doing a home inspection, I'd be like, this is partially closed. Don't mess with that. That's supposed to be open all the way. I would have no idea.
Don't open it. Don't open it.
Yeah, it's partially closed for a reason. But not only that, if somebody does mess with it, how is the homeowner or anybody else supposed to know where it belongs?
Right. So there's two things that can protect this particular homeowner or this gate valve. First, it's required to be labeled and marked at its original setting. Second, it needs to be made inoperable. In this case, what you can do is set it and then run a screw through this part so it can't get moved.
Perfect.
So that's one thing. There are ball valves. You guys are probably more familiar with that in the plumbing world, but you can set it and then mark on the pipe what the angle is on the handle. There are dampers in our HVAC systems all over, right? And that's another way that you could put a damper in one of our radon pipes is get a metal damper with a little handle on the outside of the pipe and set it. And then pull the handle off is what I do. So you can set it, and then there's like a fly nut that you can tighten. My personal favorite way to do it is if I know the orifice size that I need, I will take a pressure cap and drill a hole or a series of holes in the pressure cap, bury that in a pipe junction. So no one even knows that it's there, but I know that I'm throttling the air down, and then no one can mess with the setting here.
Okay.
Josh, where does that valve typically get installed on the mitigation system?
It's going to be below the fan, always. And then also, it's probably most common near a suction point location, but it could be anywhere. Near the suction point location, but out of the way. So let's say you're drawing off of drain tile in one foundation zone and then a crawl space in the other one. You could have 2 of these in one system. So if you wanted to push more air to the crawl space, you could dial down the drain tile part or vice versa. But I wouldn't necessarily put it in high traffic areas. Don't put it in a kid's playroom because you know it might get monkeyed with.
Okay. Wow,
This
this is fascinating.
Very interesting. I was just thinking one issue I saw every once in a while was that radon systems, the pipe on the exterior of the home would actually freeze shut with frost just from that warm, moist air from the house being exhausted up through that pipe and it being super cold outside. That moisture would condense and freeze, and then the diameter pipe would just get smaller and smaller and smaller, and it would freeze shut. And I wasn't sure if that damper was located on the outside or on the inside where it's warm, or how that might affect a potential system from freezing up.
In that case, it would be installed inside. You don't want to have it on the outside of the house.
Yeah. Yep.
Okay.
I'm curious compared to, and you may not know these numbers, but, just seeing the math of how much it actually costs, a homeowner to operate these systems because it's drawing air from the house. Is that comparable to like continuous run bath fans, basically?
Yeah. Except the bath fan's not running on nearly the amount of power that these radon fans would.
Okay. So even more than a continuous run bath fan, potentially.
From an electrical standpoint, I think that's right. But you guys could probably check me on my math as far as what the wattage are on these fans. And I will say too that commonly installed bath fans don't operate at the specs that you see on the box. Mm-hmm. Right? You guys see that too?
Yeah. Reduced flow rates and
Yeah, that spec is assuming there is no ducts, no nothing.
No resistance.
That's what's coming right out the end of it. As soon as you put a pipe on there, it drops it.
Yep, and then you kink the pipe or slink the pipe or whatever it might be. So your 90 CFM fan is really moving 30.
50.
Yeah. I wanted to bring one thing up, a funny story about the house we were working on. The kitchen exhaust fan, the kitchen exhaust hood had 4 fan settings. It was like slow, low, high, and turbo. Mm-hmm. And I want to say it was like 50, 100, 300, and 400 CFM respectively.
Yep.
We did not see a change in the amount of airflow from setting 1 to setting 4. We also didn't see the pressure change in the house with respect to outside from setting 1 to setting 4. It just got louder. That's all it did. And the homeowner complained about it. It's like, I don't even want to use the kitchen exhaust hood because it's so darn loud. So once we measured the lack of airflow change, something was up. So went on the side of the house to check the exhaust, and that was clear. The door worked well too. So we pulled the microwave off the wall, and the flapper from the back of the microwave would open up 90 degrees, but then plug the elongated exhaust duct. So the flapper on the back of the microwave was blocking the airflow from the exhaust hood. So once we took that off, now we've got 50, 100, 300, 400 CFM respectively, and it's a hell of a lot quieter, and they can use it now when they're cooking.
So is that like an internal damper you're talking about that was creating the problem? Yep. Okay. And are those supposed to be removed then for proper installation?
I think proper installation would have given it a little clearance between the microwave and the elbow on the ductwork.
Okay. And allowed for the damper to open properly and not block airflow. So because it was installed the way that it was and the connections where it was restricting airflow.
Right.
Yeah. Interesting.
Sure. I'm tracking.
So weird things you find just trying to fix radon in houses.
Wow.
Yeah.
You wonder how many kitchen fans are installed that way, right? Where they're not working properly or the way that they were designed to work.
Yeah. Sadly, maybe certainly more than we want to know.
Yep.
Well, Josh, I want to really just make the theme of this show reasons to not buy a cheap fan and do it yourself on a radon mitigation system.
Okay.
I want that to be the focus. I know we had some other stuff to talk about, but every once in a while, when we got such a good topic, I don't want to dilute it by trying to talk about a bunch of other stuff.
Hey, fair enough.
I feel like we need to schedule a part 3 if we're going to get into a whole lot of other stuff on this. Just, I've learned that writing a lot of blog posts. I gotta stick with one topic. But is there anything else on this topic that we should cover before we close this show out and maybe schedule you on for a part 3 in another 2.5 years or something?
Yeah, right around the corner. No, I think what's imperative for home buyers is that when you're looking for a radon professional, try to find one that can do what we described. It's going to be well worth it in the end. You're going to pay a little bit more up front. And sellers aren't going to want to pay for that, but buyers will. Mm-hmm. And so if it becomes a contentious part of the negotiations, just get cash at closing, get money toward it, and then maybe the buyer can cover the additional labor that it may take to do what we were describing.
Yeah.
So would some of those good questions be to ask, like, for example, what types of fans do you install? Do you have different, how do you test the pressure under the slab? What would you ask a contractor?
I would ask the contractor, how are you going to optimize the system and install only what's needed?
Okay. That's a good question.
That's really good.
Yeah.
Okay. All right.
Okay. And then where should a homeowner or someone who needs to install a system, where can they look to find good licensed contractors? Is there a resource?
She said good, Josh.
Oh, she did say good. I cannot tell who's good and bad. The position I'm in, but we have a webpage that lists all our licensees, so all of those people who are qualified to do the work. And then we have another webpage about radon mitigation systems that talks about what to look for in a good contractor and what radon mitigation systems look like. So those 2 resources is where I'd point you, and that's at mn.gov/radon.
Okay.
Perfect.
All right.
Thank you.
Well, this has been fantastic. I feel like I learned a lot out of this episode.
Me too.
Very enlightening, Josh.
Fascinating.
Thank you for coming on again.
Thanks for having me.
We may schedule part 3.
All right.
All right. Well, Merry Christmas, Josh. Happy New Year. All that fun stuff.
Thank you guys.
Thanks again. Really appreciate it, sir.
Good to see you.
All right.
See you guys.
Take care.